Alright, in part B of chapter 9.3, we are looking at two-sided tests for means. So here's the problem. Don't break the ice. In the children's game, Don't Break the Ice, small plastic ice cubes are squeezed into a square frame. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. The machine that produces the plastic cubes is designed to make cubes that are 29.5 millimeters wide. But the actual width varies a little bit. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The Fathom output summarizes the data from a sample taken during 1 hour. So here's the Fathom output, and it's a little bizarre and weird looking, but you can do this. Look, so it tells you what these numbers are right down here. This is the key. So that first number is the mean of my 50 cubes. The second number is the count. There's 50 of them. The third is the standard deviation of my x bar. And the fourth is the standard error. Remember, standard error is a little different than standard deviation. I'll clear that up on the next slide. So the first thing it asks us to do is to interpret the standard deviation and then the standard error provided by the output. So we're differentiating between these last two values. The standard deviation is that 0.09 millimeters, okay? It is the widths of the cubes are typically 0.09 millimeters from the mean width of 29.48 millimeters, right? That's standard deviation. Standard error takes into consideration the sample size. So it takes the standard deviation we have right here, and we divide it by the square root of our sample size. That's when it becomes a standard error. So standard error is dependent on sample size. So when I interpret, I have to mention that. I say in random samples of 50 cubes, the sample mean will typically be approximately 0.013 millimeters from the true mean. Okay, hopefully you see the difference. All right, B, do these data give convincing evidence that the mean width of cubes produced in this hour is not 29.5 millimeters? Use a significance test with an alpha of 0.05 to find out. So I'm going to do my state plan, do conclude. So one of the first things I have to do is come up with my hypothesis. And this phrase right here is really telling. We want to know if it's not 29.5 millimeters. So that means our alternative will be a two-sided test. It's a not equals to 29.5. That also means our null will be equal to 29.5. And it's mean, so I want to make sure to use the mu as my parameter. So in my state, it will look like this. I want to test that mu is equal to 29.5 versus mu is not equal to 29.5 at the 0.05 significance level, where, to find my parameter, mu is the true mean width of the plastic cubes. All right, easy enough. Now, the plan step. I'm going to perform a one-sample t-test if the conditions are met. First condition, is it random? Was it a random sample? If you go back and look at the question, it was a random sample. Is it reasonable to assume that there's more than 10 times 50 or 500 cubes produced in 1 hour? Yes, that's reasonable to assume. And then lastly, is my sample large enough to use central limit theorem? Is n greater than or equal to 30? Yes. And I would add on here that you would say by central limit theorem, we know that the sampling distribution is approximately normal. All right, so we've done state and plan. Let's do this. So on the do step, I've been given the values I need for my formula right up here. So I can plug them in. There's my x bar. Here's the hypothesized value. And then I put standard error down here. I put this value. So be careful. If you use the standard deviation, you would have to put the standard deviation divided by the square root of 50. So I just skipped that step. I use the standard error because that's what always goes on the bottom anyway. And I calculate t as negative 1.21. But if you recall, our alternative hypothesis is a not equals to. That means it's a two-tailed test. So my t that I calculate is negative. That means the positive version of it is just 1.21. So I have two tails. If you remember, I need to find the area of one tail and just multiply by 2. So I'm going to take 2 times the TCD and then put in my parameters. Okay, I happen to put in 1.21 to 1,000 with 49 degrees of freedom. That's what this is for. I could have done the lower end and gotten the same result. It's fine. So my p-value is 0.2 0.2321. Alright, so I just copied my p-value on the slide so we can do our conclusion here. Remember, we start by comparing our p-value to our alpha. So I would say because the p-value of 0.232 is greater than our alpha of 0.05, we fail to reject the null. There is not convincing evidence that the true mean width of cubes is different than 29.5 millimeters. Okay? So this whole phrase right here is just your alternative hypothesis. You either have convincing evidence for it or you don't. If we fail to reject, we do not have convincing evidence. Now part C, calculate a 95% confidence interval for mu. Does it support your decision from B? Well, if I calculate a confidence interval, remember my formula, x bar plus or minus t star, and here's my standard error, right? So I have x bar in the table, I have standard error in the table, I just had to find my t star. And then I calculate it out, and I get a confidence interval of this, 29.46 to 29.51. So, I'm looking to see, is my null value, the 29.5 millimeters, is that within the range of these values? Well, it is within there, so I would not reject that null. Since 29.5 is included in the interval of plausible true mean values, we do not have convincing evidence that mu is not equal to 29.5. And that's the same conclusion we had up here, right? Two ways to get there. With the two-tailed test, you can use confidence intervals to get your decision.